let me come to the concept of standard drive cycle. A standard drive cycle is standardized and standardized by some body, not normally motor vehicles authority in a country, and it is standardized for different vehicles, 2-wheelers, 3-wheelers, 4-wheelers, e-rickshaw, autos, so that vehicle by two manufacturers can be compared. That is the purpose. And also saying that, well, you are not unnecessarily wasting petrol, because it is important, because if you are wasting petrol, it is actually converted into more and more emissions. So, just like those emissions testing etcetera is done, the drive cycle tests are always done. And of course, the slogan "Kitna deti hai" has made this extremely important, because I will buy Maruti because it gives me higher mileage. So, each vehicle have its own drive cycle. In fact, different cities can have different drive cycle. Why? Because depending on the congestion in the city, the standard drive is different. It tries to typically picture a standard drive, but very often, so there is a daily drive cycle, but very often in cities you use the same kind of drive cycle in a country. Countryside, if you are mostly driving in countryside, drive cycle is different. Usually climbing a slope or climbing down is not standardized as a drive cycle, but if you are actually driving a vehicle in a place like Trivandrum, which has a huge slope going up and down most of the time, it does not make a sense to have a daily drive cycle which is on flat road. You have to define a drive cycle for Trivandrum, which will have to take into account the slope up and slope down. So, it is up, one can define. In fact, in the things that I am going to give you, while I will mostly talk about flat road, I am going to give you some examples or some assignments where I will say, let us have a slope up and down, what is the energy consumed per kilometer. Different countries have different drive cycle or different continents. For example, in Europe vehicles drive at 150 kilometer per hour. In India, they do not drive at more than 90 kilometer per hour. So, Europe will have a different drive cycle, we will have a different drive cycle, US will have different. In fact, within US also states have different drive cycles, because they have different kilometer per hour limits. It will take into account also the average roads, what are your speed limits, they are not supposed to drive at higher speed than speed limit. Normally, drive cycle is never defined for 100 kilometers, it is defined for smaller distances, 2 kilometer, 2.5 kilometer, small time, and then you keep on repeating that cycle. You take, because you do not want to take measurements on one cycle, because maybe some slight extra energy was used or less energy is used. So, you repeat that drive cycle 10, 20 times and then take the measurement. So, measurements taken over multiple cycles. With this, let me come with the first definition of a drive cycle. This is called India drive cycle for two-wheeler, it is called IDC. It is a drive cycle defined for two-wheeler and it is very commonly used. And remember that these drive cycles have been defined for petrol engine. For electric vehicles, same thing will be used, but certain things you will see there is practically no reason. It assumes that after you start, you are idling for 15 seconds. This idling, why are you defining idling? Idling means you are just waiting, 0 speed. In electric vehicle, during 0 speed, you will consume 0 energy, By the way, auxiliary things like lights etc., are never used in standard drive cycle measurements, that is extra. In electric vehicle at 0 speed will consume 0 energy. In a petrol engine, the engine is turned on, kept on, and you are consuming certain amount of energy. So, this is a part of a drive cycle, idling. Of course, today vehicles are designed more and more to consume less and less during idling, even petrol engine. They are designed to even turn off and then have a electronic turning on. Those are things there, but anyway we will not consider that. We are going to talk mostly about electric vehicle. We will assume that yes, first 18 seconds is 0 speed, and let me go through this. So, if you see 16 seconds, first 16 seconds it is idling. Then if you see you are accelerating from time 16 seconds to 22 seconds, 6 seconds you are accelerating, and your acceleration is 0.65 meter per second square. It should have been, I made a mistake here, meter square per second I have taken. So, meters per second square. Please correct this, meters per second square. Then you are actually after 22 seconds, after that you are actually decelerating. Well, here itself it is broken into two. It is assumed 16 to 22 seconds it is at a certain speed 0.65, then your acceleration slightly decreases, does not show very well in the curve. Why does it not show? Because it is not a very fine curve, but this is the important thing. Acceleration is 0.65, acceleration goes smaller. Then for the next 4 seconds it is actually speed is going down. Then there is a steady speed for a short period of time, constant speed, neither 0 acceleration for almost 2 seconds. Then you are again accelerating this part, but you are accelerating at a certain speed, then you are accelerating faster, or slower, from 0.56 you go to 0.44. Then you are again decelerating for 3 seconds, then you are running at constant speed for 4 seconds, then you are decelerating, for 2 seconds, then you are again running at constant speed, then you are again decelerating. So, this is how the whole thing is defined for 108 seconds, and after that for 12 seconds again you are idling, and or up to 108 seconds, and then you just keep repeating. So, total is defined for 108 seconds, and then you actually have to drive it 6 times with the same pattern. Total test time is therefore 6 into 108, 648 seconds. Total distance, if you travel, you just integrate this kilometer per hour, find out the distance travel, you will come out to be 3.9484 kilometer, and maximum speed is 42 kilometer per hour. This is the drive cycle. It is actually idling for about 15% of time, 16 seconds, steady speed at for 12%, acceleration for 42 seconds, deceleration for 37 seconds. This is average speed is 21.93 kilometer per hour. This is a standard drive cycle. Now, you drive the vehicle, either a electric vehicle or a petrol vehicle, exactly as per this cycle 6 times, and you compute. So, earlier actually there used to be a vehicle track in which you had to drive to do the measurement. Now, there are instruments where the vehicle is kind of made to drive, there is a track on which it is made to drive, it is actually not moving, and there are instruments which will capture all the data. What are these instruments called? Dynamometer. So, they are these dynamometer, vehicle dynos. So, what do you do? What is the mechanism that you use to now, given this, I want to first compute. I know my forces, I know my power for every speed and for every acceleration. I know my drag, I know my rolling resistance, I know my acceleration force, I know my climbing force. In this case, of course, there is no climbing. What do I do? Actually, this can be nicely computed on a spreadsheet, and I will in fact give you assignment problem to compute it on a spreadsheet. You actually can take every second or every half a second. So, 0 to 108 second, if you do it 108 1 second each. So, you take 108 intervals of delta t of 1 second. You calculate the average velocity during that. Why it may be actually increasing? If you want to not take that into account, you take 0.5 second. Number of points will go up, number of lines in a number of rows in a Excel sheet will go up, but typically 1 second with average velocity gives you very good result. So, find the average velocity, and the distance travel in that you can compute as velocity into delta t. Velocity is given by the drive cycle, average velocity for that 1 second, you can compute the delta t. You start writing down every second what the velocity should be, take v final minus v initial divided by 2, that is the average velocity. Acceleration is what? You have calculated the delta velocity every second, you divide it by delta t, it will give you acceleration, meter per second square. Every second now you compute the force. Acceleration force is more mass into acceleration. Mass of the vehicle is known, acceleration. So, you have all the 120 value of the acceleration every second you are doing that. You now compute the rolling resistance. You know your mass, you know the g, you know the value of mu. Find out the rolling resistance. You can assume mu to be constant. Also compute the drag force, 0.5 C d rho A is given, v is changing, every second it is changing. Average velocity, take average velocity and compute all of that. You go on. Now, since you have computed the acceleration force, rolling resistance, drag, this you compute what is called total traction force. You also compute the traction torque. You know the force multiplied by wheel meter. So, every second what is the torque that you require. So, you have data for every second for the traction force, you have for traction torque, you have the power consumed. It is a force multiplied by velocity. So, you already have got the total traction force, you take the average velocity, multiply that, you get every second what is the power consumed. And if there is a deceleration and you want to take that into account, take the value of r. If r is negative, then you take r into f track into v. So, r is equal to 1 if it is acceleration. If there is a deceleration, means f track will be negative, then r will be equal to 0.3 or whatever. Of course, the traction power there will be negative. So, you have to take minus of that. Then you compute the energy requirement. What is the energy requirement? The power you have got for 1 second. Integrate the power or take the power in the beginning and power in the end and subtract it, divide by 2, multiplied by 1 second, that will give you the energy. So, you have the traction force, torque, power and energy. You create a spreadsheet, and for example, I will actually do that for a two-wheeler, where I have given all the velocity. These are parameters that you have to put in the spreadsheet: the mass, g, rolling resistance, drag, rho, a, drive cycle. You can just give the name, and as per drive cycle, your velocity is changing. you have to enter the velocity as per drive cycle, wheel radius you have to define, regeneration efficiency you have to define. And based on that, use India drive cycle, compute velocity, distance travel and acceleration every second, compute each component of traction force, drag, rolling resistance and acceleration, compute total traction force, torque, power consumed, integrate the power consumed to compute the energy consumed, use regeneration efficiency to compute the energy restored to the battery only when deceleration is taking place. So, this is the kind of spreadsheet that you create. If you see, this is for two-wheeler, the IDC that I gave you, velocity is 0. So, in fact, 0 to 16 second I do not write 0, 1, 2, 3, 4. Why? Because it is all going to be 0, 0, 0, 0. So, I actually from 0 I come to 0 seconds, the velocity is 0 kilometer per hour and distance travel even in meter per second. Of course, from kilometer per hour I will convert it into meter per second. How can I do? By dividing by 3.6. So, I have to divide by 3.6 to get 0 meter per second. I calculate what the acceleration is. So, from 16, 17, 18, 19, 20, 21, my velocity keeps on changing. I take those velocity point, take the average velocity point and compute my take the average velocity point from 0 to 2.33, the average velocity is 6.6481. Between 2.33 and 4.66 average velocity I calculate, well, velocity is 2.33 and 4.66. How I made a mistake. Velocity is, and acceleration is constant. This is a delta velocity. This I am taking as delta velocity. This I think delta is not visible, it is a delta velocity. And with the average I am able to do that. So, this is what the velocity versus kilometer per hour, I can plot that. It is the same as the drive cycle, and I can also travel the distance that is travelled in each time. Remember, this distance is also travelled during deceleration. I am actually just keeps on adding the distance. This is the individual distance travel, incremental. This is the incremental velocity, incremental distance, incremental velocity, incremental distance. This is the incremental distance, this is the incremental velocity. I have to integrate to find out the total distance that I have travelled. Total distance that I will travel is 658 meter. So, remember the distance here as goes, it travels to 5 meters, then it goes down 5 and keeps on going up and down. But what is happening is that if I integrate it, it will give me 658 meter. Incremental distance is that much. These are incremental distance and incremental velocity. Okay? I can compute the acceleration. Once I have computed the acceleration, I can now compute the acceleration force mdv by dt, rolling resistance for every line, every row. I can calculate the drag, I can calculate the traction force, I can compute therefore traction force is total acceleration for rolling resistance per drag, very easily doable in spreadsheet. Torque I can get multiplied by radius, wheel radius. Power I can consume, because I multiply f track by velocity, I compute power kilowatt, and I multiplied by delta t. What is the power consumed? This has many more decimal places I have not shown, and then I compute by energy by simply integrating at 100% regeneration efficiency. I can also compute at r percent regeneration. Now, if you see the energy consumed sometime goes negative, the net energy consumed integration. Why? Because my power consumed is negative. This is the regeneration that is going on. So, I am taking the regeneration efficiency into account. In this case, regeneration efficiency is 100%. So, this spreadsheet will be able to tell me what is the energy that I consumed, what is the power that I consumed every second. I can also find out the distance that I consumed, which I did that in the previous thing, the distance that I consumed, and from here these two I can consume the watt hour per kilometer. I am showing the same thing in this side, this energy comes here. So, I am hidden part of the, I have taken this part of the data and then I also take the data more. And if I see this, I am here plotting for the whole, I do not have 108 rows, I am only showing limited number of rows, but I am actually plotting for all of the 108. What is the energy consumed in every energy consumed? Energy consumed. How is the energy consumed? Going up and down. And I find the total energy consumed for 100% regeneration is about 7.441 kilowatt. That is the total energy consumed. If you see, energy consumed keeps on building up, but it goes down. It goes down. Why? Because it is actually decelerating. In the end, it is decelerating. So, this is the regeneration efficiency energy, and regeneration energy, since I have consumed made it equal to the SL R equal to 1, it considerably goes down. What if I do not take R equal to 100%, but if I take R less? So, R equal to 0.5, if I assume R equal to 0.5, what happens? Whenever traction force is negative, else R is taken as 1, otherwise it is R equal to 0.5. So, energy consumed is same, P track and delta T, regeneration recovers only part of the energy. My total distance travelled remains the same, 658 meters, but now look at this red curve. Red curve is assuming, red curve is with a 100% regeneration, blue curve, it is slightly higher. By regeneration, see, in the beginning it is the same, but regeneration does not recover the full, it is only recovering 50%. R is I have taken as 0.5. So, it is not recovering full, 50% if it is recovering, I am consuming more, I am consuming 8.78 watt hour in 658 meters, my average energy consumed is 13.34 watt hour per kilometer. If I took 100% regeneration, actually I consume less, 11.31. If I assume no regeneration, then my curve will be different, I am not shown there. Instead of 50%, if I consume no regeneration, the negative part will not come, it will come as flat. It goes up to 15.38 watt hour per kilometer. What do these numbers tell you? These numbers are very important. This is actually for a low speed two wheelers, India drive cycle, India drive cycle, low weight, 180 kg, 190 kg is what I have assumed. Actually, you need to consume, even without regeneration, about 16 watt hour per kilometer. Of course, I have made a number of assumptions here. This is as per theory, assuming that as all the forces. In reality, what happens? Well, I should get pretty much close to this, very close to this, because my rolling resistance is actual, my drag is actual. What is non-ideal is motor. There is a loss in the motor, I am not taking that into account. There is a motor controller, there is a loss in the motor controller. So, the losses I am not taking into account. So, to the extent I am not taking into account the losses, that much energy consumed will become more. So, if I assume that there is 20% losses, which is somewhat high, my 15.38 may go up by another 3.2 watt hour. So, 17 to 18 watt hour without regeneration. With regeneration, depending on the amount of regeneration, I should be 15-16 watt hour per kg. Another thing that I am not taking into account is auxiliary, is the light on. So, if that whenever that is turned on, there will be some extra energy consumed. But we are still a light two wheeler should not consume more than 20 watt hour per kilometer. A good one may consume 16-17 watt hour per kilometer to 20 kilowatt hour per kilometer. That is what I can, even from computation I can tell you. This I did for a two-wheeler. I will stop here, and in the next class there is an assignment. The assignment is pretty much what I did. Prepare a spreadsheet for two-wheeler IDC with the data that I have already given. Obtain the traction force, traction power, torque every second, and compute. This time I am going to ask you to compute for r equal to 0.3. You cannot just copy the results that I have produced. You actually have to build this spreadsheet. This is an assignment that I am going to give you. You have to build it. It will take a little bit of work. It will take you about an hour, 2 hours of work, but you will find that you will be able to actually do this. Now I am going to change the drive cycle. And I assume that 100 seconds in the first 100 seconds in the drive cycle is exactly what I defined for IDC. But after that it climbs a slope at 5 degrees for 10 seconds, climbs a slope, and then the vehicle is taken to 0 speed. Climbing it at a constant speed, I have taken it at a low enough speed, then the vehicle goes to 0 second, just like in IDC. So, I have changed your drive cycle. You add that in your spreadsheet, change that. Now, this extra, take a copy of that spreadsheet and add a few rows saying it is now climbing up. Add one more force, the gradient force. Nothing else changes. So, traction force is the previous 3 plus gradient force, and compute. This is a home assignment. If you do this, you will actually get a very good feel for everything we have done so far, because it includes all the forces: acceleration force, the force due to drag, force due to slope, force due to rolling resistance. It tells you how to compute the total force. It tells you how to compute the torque. We have not talked too much about the torque, but we will talk about torque some other time. It tells you what is the energy, power consumed, and every second energy consumed. Of course, assuming motor and controller and batteries to be ideal. If it is non-ideal, we will look at it. Actually, to sum up, a low end two-wheeler consumes only about 16 watt hour per kilometer without taking into account regeneration. As I told you, with 50% regeneration gives you very good result. So, it can travel 70 kilometer in 1 kilowatt hour. We will assume that 1.25 kilowatt hour is the actual battery. We are only using 1 kilowatt hour of that. So, it can actually give me 70 kilometer with regeneration, but if the regeneration is not that good, it will not give me. But as I point out, computation does not take into account assumes that every element of the drive is ideal. Inefficiencies may add up to around 20%, and it does not take into account the auxiliary energy used. This is where I will stop, but in the next class I am going to talk about e-auto, e-cycle, e-rickshaw and compact sedan. Pretty much repeat what I have done today, but with slightly different numbers. But you will get a feel of these 3 vehicles also. Exactly the same. Drive cycle may change or may not change. If it changes, we will give the new drive cycle, and does do that. This is what we will do in the next lecture, very similar to what I just now did for two-wheeler. Now, I will do it for e-auto first, then for e-rickshaw, and then for a compact sedan. After that, we will do the same thing for a small truck.